Hello everyone. We're going to start looking at malloc again, and we'll pick up where we last left off. So last time we looked at things, we were asking for an array or just a big chunk of memory from the operating system. That's what malloc does. It's memory allocation. So you ask for an address of memory that you can put stuff into. You say how many bytes you're going to actually need, and we get a certain number of bytes of memory, and then we cast it so that we get different sized buckets. So we say, I want an array of integers, and now I know how big each of these buckets are. The same number of bytes of data, so I may have 64 bytes worth of data, and now I'm going to break it down into chunks of 4 bytes at a time. Or for characters, chunks of 1 byte at a time. So an integer takes 4 spaces, a character takes 1 space, and so the first number of characters, essentially it is 4 times, each bucket is 4 times the size for an integer than compared to a character. And then once I got that, I'm free to go. I can just use it like my static arrays. I could say, my buffer at position 3 is equal to character C, and I'm good. I don't have to worry about, oh, well, it's a dynamic array. You access it and use it the same way as you did the static array. Except, yeah, there's always a gotcha in there. It is not automatically given back. So if you call malloc, you must call free. Just get in the habit. It is the big problem. It is pointer issues, null pointer exceptions, missing semicolons, and not freeing your memory are some of like the big things in all C for C programmers when they're learning. And in industry, one of the big problems for everybody, no matter how many years of experience you have, is not freeing your memory. It is to the point that in other languages like Python and Java, they knew it was such a glaring problem that people had that they do it for you automatically. If you stop using that array, it is automatically given back to the system. It's called a garbage collector. They have some other process in your system when you run your code, checking to see if you're no longer using that array, and when you stop using it, it gives it back to the system automatically for you. Because it was such a glaring problem, and yet C still has it. And if you want fast code, you still need to do this. Garbage collecting is actually slower. You are relying on the system in its infinite wisdom to realize when you need to give back resources versus you control when you give back resources yourself. So one of them is, to go back to the library metaphor, you took out a bunch of books. It's your responsibility for giving them back. Java says the library is going to come to your house and steal back the books whenever they feel like it. Right? They think you stop reading your book, they're going to come back to your house and take the book back. Some people may not like that because you also don't know when they're going to come back to pick up the book. You might have a messy house at the time. So you need to call, but we're doing C, you need to call free when you're done with your array. So we're going to look at free in a second, but I just wanted to address the elephant in the room here. You might see something weird on my part. This is not universal. This is not something you need to do. It is something I like to do. I liked it. I thought you might like it as well. And that is, we have naming conventions. And my naming conventions here are not necessarily universal for all people, all times. In C and C++, though, I find my particular naming convention extremely useful. So, this is not universal, but we have, for a particular variable type, if I have something that has returns a true or false statement, like has ID, or has master sword, or is female, or is injured, or whatever the case is, something that is a true or false statement for a function, I will often use is or has as a convention to indicate what that function is doing. Has master sword as a function tells you if you have the master sword or not. My variables might be called num, or if I have a counter, I might call it count as pretty convention. I do it all the time. I have retval for return value. I have PTR and IDX. That's very common for everyone. PTR standing for pointer, IDX standing for index. If I don't want to just use I is for for loops, right? If I just want the index itself and I'm not using a for loop, I will use IDX. For member variables, when we're doing objects later on in 2400, I'll use an M underscore. For global variables, I might use a G underscore. Not always the case. I use all caps when I have a constant that I know I can't change. The one for me, because I have such a horrendously bad memory, is I use A underscore and P underscore. Because at the end of the day, there is no difference between a pointer and an array. An array is I get a chunk of memory, but all I get is the pointer to the first of that memory. There's no way for me to know if it has a single element or if I have a bunch of stuff. I could have one thing or I could have 20 things. And so for me, and the only reason I do this is if I want to clearly indicate that this thing is an array and not just some variable, not just some pointer, I will use the A underscore to say this is an array of values. And it's easy enough to forget the S to pluralize things. So my nums, if I call it my num, it's suddenly a singular. A underscore, I know it's an array. P underscore, my nums, is a pointer to some variable named my nums. There's nothing forcing it, my nums, to be more than one thing. And so it avoids some of the confusion because this is a pointer, this is a pointer. We're going to look at pointers very soon. They are one and the same. The only difference is I need to know that there's more than one element with an array. I don't, and with a pointer, there's one element. So one element, multiple elements, and the only way I can tell the difference is I name them slightly differently. So you don't have to follow that pattern, but I like that pattern simply for my own peace of mind because I'm ridiculously bad memory. Okay, let's go over the free operator. It is not getting things for free. It is the free operation. All you do is call free, and you put your buffer in there, or you put your array in there, right? I made an array called a buffer. When I'm done with it, I call free and the name of my array, and presto magic, it frees up the reserve. It gives back the memory to the operating system. Free actually knows how big the array is. I find this fascinating. It knows how big the array is, but never allows the programmer to ever know this. So they do have some hidden little bit in your array when you get it for how big that array is, but you do not get access to this at all. You cannot ask the array how big it is, but the operating system and your compiler do know. There is no way of getting it any other way. I find that weird that they didn't expose that to people. So it's a hidden extra feature in your every single array that you make. So it acts like magic. All I do is say free, and I pass in my array that I'm going to be freeing up, and it's freed. So here I'm making an array, a buffer. It's an array of, well, the size of a character times 16. It's an array of 16 characters. And when I'm done with it, I can call free and that array, and I'm good. Now the question is, what if I put the line below? This is just a pointer to this sort of thing. It's just an address where this array is. So I have, let's make it look like this actually. Boom, 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 boom. I have a pointer to this. The free operation does not change that pointer whatsoever. The free operation simply says I'm going to give this entire array back to the operating system. ABUF is still pointing to this location. When I've done free, it's still pointing here. Nothing has changed. So I make an array, I point there, I give back the array, ABUF is still pointing there. If I then say go to position 2, make it C, now I'm dealing with somebody else's stuff. I've given this back. It's like me selling my house, not giving back the key, and then coming back a couple of months later, walking into the house again and just, I'm going to take this, right? It's somebody else's house. I've given back that array. I need to not be getting access to it anymore. So I am perfectly capable of writing something like this. So, and this was a regular problem. So when people were doing this sort of thing, this problem came up again and again, and so we have a workaround. The workaround is, instead of pointing to this, what we do is we cross this off and say point it to null. Null is effectively like pointing it up or pointing it somewhere else. You're not going to that same location in memory. You are just pointing to some other place, the void, if you will, right? The place that does not have a memory address. In fact, null is exactly equivalent to the number 0. I'm pointing to 0. The address where I'm pointing, 0. There's no memory at position 0. The reason I do this, so when I'm done, I say A is equal to null. The reason I do this is if I do this and then I try and access a buff, if I try and write this line here, I'll get a null pointer exception. My program explodes. And you say, why would I want my program to explode? And I say, you want your program to explode rather than stomping on other people's stuff and not being aware of it. I don't know if this is useful, but I'm watching Modern Family with my wife right now. There's an episode of Modern Family in season 2 where Phil and Claire accidentally, there's a key card exchange thing where they're having a romantic rendezvous, and Phil's in the wrong room. It feels like that. If you go in the wrong room, bad stuff's going to happen, especially if you're naked on the bed. So, as a general rule, when you are done with something, you give it back. You do not keep hold of it. You do not, sort of try and just in case. If you give that array back, you do not have access to that data anymore. And if you still have access to that data and sometimes you're able to do this, you start stomping on this particular value right here, you're stomping on somebody else's code or your own code used somewhere else. That's a memory stomp. And those are infamously hard to deal with. The worst thing, I get a bunch of memory, I give it back, some other part of my program takes that same chunk of memory, so I still have write access to it, and then my code starts stomping on other code in my program. So I have another array and I'm just stomping on it. And I don't know I'm stomping on something I don't have the right to stomp on. So I have a bunch of student IDs, let's say. I get an array of student IDs. I get an array of, let's say, rooms. I give back the array of rooms. And then I get the array of student IDs. But the array of rooms, I'm still pointing to it. So I now start stomping on student information and putting random garbage in the student information. That's the reason you have this null. Because what I want is, I want it to blow up there so I find my bug. Because it will take days to track down what's causing me to randomly get my data stomped on. It's just random data changing on me and I don't know why. Because somebody else has access to that same piece of memory and I don't know. It's ridiculously hard to track down. Okay, so that's why every time we give back our array, first thing we do, set it to null. We set it to null to make sure that we don't, it clearly indicates I've given it back. How do I know I give it back? It's pointing to null. So it's pointing to null, I know I've given it back, and I'm not allowed to play with it. I check to see if it's null, and if it's not null, then I do something. If it is null, I stop what I'm doing. And if I try and access it, I get a null pointer exception. That's actually a good thing. If I try and access that element, a null pointer exception is what I want because it tells me I did something wrong there, where the problem is, not 4 hours late, not some other part of my code where I think it's the wrong problem. So this is actually a very good thing. And our workaround is this. All I do is say, hey, is a buffer not equal to null? If it's not equal to null, I can do my stuff. If it is equal to null, don't. So here is a buffer again. I could also, instead of saying not equal to null, here's my shorthand. If a buff. Why? Because if it's equal to null, null is equal to 0. So if it's not 0, go ahead. If it is 0, then stop. This is the reason I had to point out why false and true are not 0 and 0, right? Because of this. You will see this in people's code all of the time. If I'm dealing with a pointer, I'm dealing with an array, dealing with anything that could be null, I'll put things like if, and then that pointer or that array, if that. And you go, what? How is that a true or false? It's either null or it's not null. If it's not null, it's free. You're free to use it. Okay. We'll get to dynamic arrays soon. I'm going to abstain from looking at the code right now. I'll make that as a separate video. I want to get to CALLOC. So here is, we should be going back to dynamic arrays right now. We're looking at CALLOC, and then we're going to go through code because it's easier with these kinds of videos. CALLOC sounds like Kellogg. I don't know. CALLOC is a different version of MALLOC. It is, I can't even remember what it actually stands for. What the C stands for. It is clearing allocation of memory, I do believe. Um, it has a slightly different format. It looks just like malloc. It returns a void pointer just like malloc, but the difference is, I say the number of bytes I want, and this or the number of things I want, like say the number of integers I want, and the size of each integer. I pass in two variables instead of one. I don't do the math like I did before. I pass in the size of whatever data type I'm using and how many of those things I want. And so it's going to look almost exactly the same way. The only difference is I don't have a star, I don't have an asterisk to do the multiplication. But I need the number of items and the size of each item. Wow, you don't have to do math. Meh. Okay, you don't have to do a multiplication. Fine. What is the difference? CALLOC initializes the array to save values. That's the reason some people swear by using CALLOC all the time. I'm on the fence with this one. So here's what CALLOC does. It will say, okay, you want an array of 400 elements. I'm going to set all 400 elements to some safe value. Maybe it's the value 0 everywhere. And then I'm going to give you the array. Now, if you need to go through that array of 400 elements and set all of those values to something, well, you don't need to CALLOC because you're going to go through the entire array and set those values one after the other, like what we did earlier with the setting all the 64 bytes of memory with like the number 30. CALLOC will clear things out for you, and then you can use it. So here is the metaphor. In fact, this is actually what's going on with malloc. When I ask for memory from the system, when I'm at least not in debug mode, when I'm in release mode, when I have commercial level software, and I ask for memory, I will get whatever was in that memory beforehand. Nothing gets cleared out, nothing gets saved, nothing gets like cleaned up. So I ask for an array, and I could get an array of whatever was there before. So you give me, somebody writes a bunch of stuff, puts in an array, gives it back to the operating system and it's not cleaned out, and I call malloc. Somebody or some other process now has access to your old data. It's whatever junk that was there. And like I think it's Storage Wars is an old reality TV show. Like Storage Wars, there could be some treasures in there. There are ways to hack a system as a result of this, because it passes back this this array of data that could have something important in there. You don't know. You're just getting gobbledygook. You're getting whatever was there before. The other part of this is, if you were not going to clear your data yourself, if you're going to accidentally forget to clear your data, you better call CALLOC. CALLOC cleans out the storage bin. It cleans it out and gives it to you. Versus when I go to get a storage bin, if I had this when I rented a storage unit for when we were moving, if I got this when I opened the door, I would have been pissed off, right? I got to clean this thing out. Now, if you're going to clean it out anyways, okay. But if you weren't necessarily going to clean it out, if you want to make sure you have safe values, CALLOC is the way to go. One way or the other. You should be able to use both, but they have two different uses. The reason why would you use malloc? So I think that's on the next slide. So what would be the point of using CALLOC instead of malloc? What would be a potential point? Why would I actually, let's flip it around. Why would I use malloc at all? Why not just use CALLOC? This cleans things up. Well, if I have an array of, let's say 2 gigs. Okay, CALLOC has to clean off 2 gigs of data. If I was going to already fill things in, or if every time I use something, I made sure it was set to a safe value before I got to use a particular part of my array. If I knew I was not going to accidentally use old garbage data, malloc is a way to go. It just means, so CALLOC will be slower because I'm cleaning off the array first. If I know I'm going to walk through my entire array and put values in every single one of those spots, malloc is the way to go. I don't have to, if I'm going to clear it off and then refill it in with new values, why not just refill it in with new values and avoid the clearing? But if you're not sure, go with CALLOC. It's a safer way to go. It's just a slight bit slower. So I want to go over an example, make an array of num nodes of integers. Okay, so we're going to go do a CALLOC example next time around. I want to just see if I have anything else here. And we're going to have a quiz as well. So I want you to try to make an array So you could try this on your own. We're going to go over it ourselves. We're going to get the number of nodes that we want and we're going to make an array using CALLOC, an array, and MALLOC as well, an array of integers with num nodes in it. Okay, and so we're going to get the number of nodes from the user and make these dynamic arrays. And then we're also going to give back those dynamic arrays at the end. We'll look at that code next time around, and then we'll do a quiz. All right, thanks everyone.